uw.ca or at uw.ca. It doesn't really matter. Let's see. So Leanne will presumably she left some piece of paper with details. So you put your name. Right? Let's see. So what am I gonna expect you to know by now? It would be great if you had a quantum field theory course. So how many of you have not had a quantum field theory course? No, that's great. So how many of you have not had any experience with GR? That's to a late extent, but general relativity. Is Wald your favorite Bible? No? Okay. All right. So basically, you have to think of it this way, that it's going to be almost like quantum field theory class. And we're going to go into studying 1 plus 1 dimensional quantum field series with special properties. And what I find very exciting is that by doing that, we will be able to interpret results that has some nice implications. Okay, good. So we're done with prerequisites, and well, I will try to be as detailed as possible, and if there will be a need, I'm happy to go into something that you guys haven't seen, forgot something. I'll try my best to go into those stuff more detail. Let's see. So the books that I'm going to use is the one that I learned string theory myself. I like that book a lot. That's by Polchinski. It's a little bit hard reading on the first cut. If you didn't have string theory before or didn't read anything before. But the way I look at this, my purpose here is actually to fill in the blanks. So there will be some statements, something that I struggled myself when I was in your shape and tried to go through all the, filling in the steps in between. So now I can do it much better after about 10 years. So I'll try to do that. So I think the most important thing is my webpage. Well, I mean, I don't think there probably will be nothing other than, but you know my webpage. I'm not going to write it up. Right? Okay, so you can go, and there is a link with a course outline, which is what I just copied from Polchinski book, volume 1. So a textbook. Textbook by Polchinski, and it's going to be volume 1 only. And in fact, it's not going to be the whole volume 1. And the reason is, I will try to do as fast as I can. And if you guys are going to help me, I love this. I love this. I love the textbook. So if we can finish it all, that would be great. But realistically, that's what we're going to do. So we're going to talk about. Okay, so what I think we will do realistically in this course, at least, I'll show you what is. If I ended there, it will make me unhappy. But at least my hope is that I'm not going to teach you string theory, so that you will go and start doing research. That will be impossible with this short course. But what I want to do, I want you to get interested. Meaning that I want you to know absolutely everything or understand everything that I will explain. In particular, how does two-dimensional worldsheet theory, how do 1 plus 1 dimensional quantum field theory related to 10-dimensional theory? Why it is 10-dimensional? Well, in our case, it will not be 10, it will be 26-dimensional. I'm not going to go into all the philosophical things involving landscape. That's something that I never worked. I don't intend to, unless there will be no other problems in physics at all. But realistically, so first we'll go through sort of first look at strings. So we'll try to do canonical quantization and sort of bird's view. So just action principle. Action principle and, if you wish, light cone quantization. Of point particles in strings. Right. So the reason, so this light cone method is something that will give us the fastest way possible to figure out what's the physical spectrum. So we'll study two-dimensional objects that fluctuate in an ambient space. And to get the spectrum of fluctuations, this light cone quantization will be the fastest way to get there. And if you haven't seen this before, that's why the point particle come in. So we'll do it first in the case of a point particle, and then we will do it for a string. And the remarkable thing that we will discover is that, so if you start writing down a free series, say of point particles in ambient space, there is no constraint that those series put on what's the space you put it in. Now this is different. We'll find out that that's different with the string series. And in fact, the string can consistently fluctuate only in certain space-time. And in our case, it will be a space-time of 46 dimensions. So that's, you're going to learn it right here. So here, what we're going to learn is a critical dimension of bosonic string. Okay. So again, the idea here is just to give you as quickly as possible to display this really what I think marvelous relation that asking for a consistency of quantum field theory. We need to quantize it because another thing that happens here is that the effects that we are talking about, that the dimension of the space-time is fixed, is not a classical phenomenon. So it's depend on quantum effects, and we will learn why and so. Right. So then. And of course, there will be a lot more, all possible strings. Well, not possible. We'll discuss closed and oriented strings, the spectrum, blah, 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 all that. But I'm just going to use a highlight. So after that, we're going to talk about conformal field theory. So the difference between light cone masses and conformal field theory is that it will lead us to a covariant quantization. Okay. And so we'll spend quite a lot of time. So this, in some sense, will be a course in it. So we will learn, various aspects of two-dimensional conformal field series, operator product expansions, all that stuff. So it should be fun. And actually, I think that could be useful in various other aspects. And a lot of intuitions that you will get from this two-dimensional conformal field series, some of it will get extended later. And so those of you who will continue learning string theory and get to ADS-CFT, a lot of intuition that, well, again, this is still a conformal field series. It's in 4 dimensions that you will be studying on the field theory side. And well, there will be differences, but a lot of intuition that you will learn there extends. So then what we're going to do, so here we did the quantization of the string in a light cone, and then we're going to write down a path integral, and so we'll do quantization using Polchinski path integral. Called path integral. And so the important thing that the message that will come up here will be that so what we are interested in as physicists is when we scatter the particles, what is the amplitude of this process, right? So what's the probability that there is certain outcome of the experiment? And so what we will show is that the amplitude of space-time processes, like scattering, here is E equals 26 dimensions, are actually related to correlation functions of two-dimensional quantum field theory. Of worldsheet theory. Right, so what I mean by this worldsheet theory is a theory that describes the fluctuation of the string. Okay? And so again, if you think it's quite remarkable that you ask the question about, say, gravitational scattering in 26 dimensions, and the answer that you get is what you have to do, you just have to study a little bit deeper this the 1 + 1 dimensional quantum field theory on the worldsheet of string. Right, guys, so after that, so we'll go into, so in Polchinski proof, there is the string theory as matrix. I'm not sure how much, and if we actually go there, I might explain something, but I will try to skip it, or at least not spend a lot of time. After this, what I want to do, I want to talk about the tree-level amplitude. So this is kind of giving you some practical tools and see exactly how it's going on. If you have a tree-level scattering in the space-time, how exactly go ahead and do the computation. And for example, how do we compute the scattering of gravitons? Okay, using the techniques of 1 + 1 dimensional quantum field theory. So this is what's going to be tree-level amplitude. Okay, so then in Polchinski loop there is a one-loop amplitude, and I'm going to skip it in this first pass. So if we'll have time, we'll go back and we'll ask the questions, what are corrections, and you will see a funny way. There are different ways. So if you do quantum field theory, right? So there are perturbative corrections organized. Typically, you have say one couplet, right? And well, there is some small parameter, and perturbative expansion is organized in a power series of this perturbative parameter. Now, in string theory, what's happening is that there are actually two different expansions, two different perturbative expansions. One expansion is related to so you have a string worldsheet. It's a two-dimensional object that fluctuates, and there will be a scale, right? So there will be a scale in the problem, so what we can do, we can actually try to set up a perturbation theory so that we concentrate only on very light modes, only on very light fluctuations of this string worldsheet, which have very low frequency. Okay, so there will be a perturbative expansion in that, and then on top of that, there is a different type of perturbative expansion in string theory, which is the string worldsheet might have different topologies, and it just so happens that the more complicated topology you have, if the strings are weakly interacting, then the contribution from these higher topologies come up at smaller and smaller order. So there is a different way, but you have to understand the following things, that we will have a different conformal field theory, right? So conformal field theory will be defined on the worldsheet. And so we'll have a different CFTs depending on what kind of topology we will put in. And so that's why in string theory there are these two different organizational principles in perturbation theory. And so the part that I'm going to skip is actually this one loop amplitudes. It's related to corrections due to contribution of this more complicated topologies. I'll go back. I'll go back if there will be time. So now, after that, is that we're going to talk about toroidal compactifications. And T-duality. So one of the reasons why we talk about toroidal compactifications is that we would like to relate whatever we're going to compute to our world, and we don't live in 26-dimensional world. So we have to deal with that, and so one way of dealing with that, which I'm sure you have heard, is to think that additional dimensions actually curl down. So there are small circles in our course. There will be small circles, and because they are so small, we just don't see them. And so that's what the word toroidal compactification means. So what we will see what kind of effect trying to compactify these extra dimensions, some of the dimensions of 26 spacetime, will have on the spectrum of our string. And then what we will find out, we will discover a beautiful, one of the beautiful aspects of string theory, features of a string, and the idea is that you might have, again, if you just a field series, your intuition would be, well, I can make a circle as small as I want, right? Well, there will be a different series. There is nothing, you know, there is no limit in trying to, roughly speaking, make a circle of zero size. So what we will discover in the context of studying string theory, in particular this T-duality idea, is the idea that if our circle has a radius r, then the string theory behaves in such funny way, it reorganizes itself, that a string theory on a circle of radius r will be related to a string theory on a circle of radius r prime, which is ls squared over r. So this is like the fundamental scale in a string theory, if you wish. But you have to think what the implications of that is. So that's what we will learn when we will talk about T-duality. So the implication of that is the idea that there is some minimal length in some sense, because, you know, if you ask the question, so can the string probe spacetime if we think about the string as a microscope, can the string resolve the spacetime up to zero size? And at least the models of the strings that we're going to study, the answer is no. Okay, so the string can resolve the spacetime only up to a length scale of order. So, well, you know, you can see that the smallest radius possible is actually the size of the string. But then that shouldn't surprise you, right? So if I try to see how big is my space, okay, if I try to see how big, you know, some sizes, if I want to use a string as my ruler, and my ruler has a size L, I cannot measure anything smaller than that. Okay, so in other words, in our course, 1 centimeter, or whatever the smallest distance we're going to measure, is going to be this L string. But of course, we are all interested in what's happening with the space on my smaller dimensions, on my smaller scales, and strings are not a good microscope to look at that. And so the good microscope to look at that, and that's also what will fit nicely with this, is actually the idea of D-branes. So D-branes are another objects in string theory. They are not strings. But those are the objects that would allow us to probe space on much smaller scales. And so besides T-duality here, we will talk about D-branes. Okay, we'll talk about D-branes, and yeah, I guess that's the most important thing. And that was one of the biggest discoveries in string theory, again, due to Joe Polchinski. And we will see how, this is something that you will find over and over. What differentiates string theory is that you are not putting anything by hand. Rather, what is happening is that you study the theory and you are forced to do that. Otherwise, you are getting garbage. So what we will find out is that first we will get convinced and understand why there is a stereoduality. And then we will see that once there is a stereoduality, and once we say it must be in the theory, then you are forced to talk about the degrades. Okay, you are forced to talk about the different objects. So unlike strings that we're going to study, those are extended objects that we're coupling, but those are very important objects, and they led to a lot of further great developments in string theory, became known as string revolutions. So in particular, there are regimes in the string theory in which those objects are more fundamental in some sense than the strings that we study. Also, those objects are the ones that are very popular in cosmology right now. So people that talk about brain world cosmologies, if they want to do it in string theory, which is where those things are being predicted, what you deal with a deep brain inflation. So that's another kind of buzzwords that you have heard probably. And finally, something that a lot of people are excited right now is the correspondence between gauge series and string series. That's a correspondence that involves deep brain. Okay. Also, some aspects like counting the microstates of a black hole, of extremal black hole, we are back again. So that's where deep brains are important. Of course, I'm not going to count any of that for various reasons. One is probably I'm not good enough to do that. But seriously, another thing is that it will be too long. So we'll try to see how much we can get in. But so this is, if you wish, the minimal thing that I would like to do. And well, if we do all of that, then we'll decide. You know, you guys are more interested in something, we can go into more advanced stuff, or we can go and kind of go back and ask the question, what about loops? Okay, and we'll just do one loop, which is also a lot of interesting phenomena. What we're not going to study, well, okay, or alternatively, we can say, well, this bosonic string. We will all find out probably as early, actually not probably, but actually as early as here is very safe. I'm tempted to say incurably safe, but I'm not going to say it. Well, the problem is that we'll see that there is when we study the spectrum of this theory, is that there is a tachyon. What this means is that there is a field. So the string theory, the excitations of the string theory will be described by certain fields that live on the wall volume of the string, and one of those fields will end up looking something like this. So it will have a potential of this type, which means, and where we will be sitting at this point. So there will be some field phi. And so what we'll find out in part one, that in the string series that we discussed, which is a string theory, a bosonic string theory that has only, well, we'll talk about extensions to fermions on the wall sheet, but has only bosons on the wall sheet, then what will happen is that one of those fields is actually a tachyon, so it's unstable. So what we are talking about, we're doing an expansion and we study theory around an unstable point. And we all know what will happen, that any smallest quantum fluctuations will try to force that field off the top. So similar situation happens in standard model, right? So when we have a Higgs potential and there is a, well, there is a series with spontaneous symmetry breaking, So usually what happens is that the potential has the shape of the Mexican hat. And so if we are sitting up here, well, we know what must be done. We have to find the true minimum. And once we find the true minimum, we have to do our quantization and have to do all the work back in this new stable vacuum. So in a closed string, again, so I'm going to use words which I didn't explain for now, but in one of the string series that we're going to discuss, well, there will be tachyon in all of them, but in particular in a closed string theory, and a closed string theory is very interesting because that's a series that contains gravity. Okay, and so when people talk about theory of consistent quantum gravity, or theory which allows to quantize gravity, you're forced to talk about closed strings, okay? Because your graviton is in the spectrum of this closed string. So what happens is that this theory, the bosonic ones that we're going to study, as I told, besides graviton, has this very ugly field. It has a tachyon, and what we don't know what's happened here. Okay, so we don't have an understanding what's the analog of the right vacuum. So if the situation would be like that, and it was like that when I was in graduate school, at least that's what I heard. So it would be pretty, well, I mean, that's what I heard, the situation with my faculty. There wouldn't be much of the string theory, right? So it's hard to make sense about the theory which is unstable, and so there are ways how you fix it. And one way to fix it, and actually, I would say in the case of closed strings, the only way to fix it is to require supersymmetry. So you can take a perspective here is that a string theory predicts a supersymmetry. It requires it. If we want to take this theory and make sense of it, and all the beautiful stuff that I was telling you here, counting the black hole entropes, relating to strongly coupled gauge series. So if you are forced to get rid of this field, you have to actually extend your theory and enlarge the symmetries of your theory, including supersymmetry. So that's why, and I would say that's a fair remark when people are saying that that supersymmetry is being predicted by string theory. So what happens is that, of course, it's naturally then that once you have supersymmetry in string theory and you build up models of particle physics built on string theory, that those models will come supersymmetric. And so that's why people are very excited and looking forward to LHC to see if there will be an inclinations of supersymmetry. I have to say up front that if the supersymmetry would be discovered at LHC, and some people believe very strongly it will not be a proof of string theory, but it will be a very strong indication that we're on the right track. So it's a very beautiful symmetry, and as I try to motivate here, it's important. Without it, the string theory doesn't make sense, as we know. So that's what I'm not going to talk about. Okay. So and that's part 2. That's volume 2 of Polchinski book. Okay. But again, you guys are good, and we'll do all of this. Right. And we'll see. We'll just go and do a bit of super strings as well. That's why on PI website we are not string series, we are super string series. Okay. So in reality, I should say that most of the stuff that I work, and in particular in the context of ADI-CFT correspondence, I do work with, so it's a supersymmetric string theory, but I work only with the bosons of that supersymmetric string theory. In some sense, I need supersymmetry only to have a warm feeling in my heart that, it's a consistent thing to have, but if I do some specific computations, I don't usually touch fermions. Okay, so I deal with boson, and there are various reasons for that. So one of the reasons, so again, it's not like I'm trying to do some black magic or something. For example, if you're interested in questions, you know, how does your model look like at finite temperature, right? So that's something that will be related to black holes. And so typically at finite temperature, fermions are much more heavy than bosons. So there is a natural separation of excitations, and so I'm just studying the light excitations, which is what the quantum field series like to do. They like to write down their theories that describe the interaction of light fields. All right, having said that, so any questions now? No? Great. So, let's go. So I'm going to introduce a bunch of conventions, and I'm going to introduce these conventions as we go. So the most important convention is that we're going to study string theory in the Minkowski spacetime. We're not going to say how many dimensions it has. So it will have d dimensions, but the metric is -1. That's my metric conventions. -1 plus 1 plus 1. So there is d minus 1 pluses, and there is 1 minus for the time direction. So something that I did not emphasize, the string theory doesn't have any free parameters. Okay, so that's another beautiful thing. You want from the theory that ideally, the approach of string theories is to have hands off, so you don't want any parameters. However, you are forced to have one, and that's a scale. Okay. Otherwise, if you measure any physical process, it doesn't make sense to say. You have to say, you know, what's your 1 centimeter? What's the size? You know, or what's your energy scale? It's in the same sense as you have to have your ruler. And so the ruler in a string theory is alpha prime. So alpha prime is defined by the size ls squared, right? So this is just a convention there. Right, so ls has the units of meter. Now, by the way, I'm working in units when c equals h bar equals to 1. And I'm not going to talk about finite temperature, otherwise I would have put the Boltzmann constant to 1 as well. So this alpha prime, and the reason why it is alpha prime is because it's related to a tension of the string, right? So by the way, so in these units, the energy scale, so the energy has the same units as inverse length. Okay. And so the tension of the string is 1 over 2 pi alpha prime. And that's the 2 pi is just a convention. And you can see that it has the right units. So if I ask what's the energy in my string, I will take the tension of the string. So this is energy in a string, right? So if the string has length L and it has tension, so that's what the energy that's being stored. So you can see that it has the right units, right? So it has a 1 over L, and with our h bar c equals to 1, it's right. All right, so very good. Let's go ahead and talk about action for the string. So I'm going to start with the point particle, and we'll use analogy of point particle and go to discuss string. Action. Suppose. Okay, so we're going to consider classical mechanics, and then we'll quantize it. We're going to look at classical mechanics of point particles in the space-time dimensions. Right. And so this particle will have some trajectory. Okay, so here are my spatial coordinates, x1, x minus 1. And so this is my time, x0. And so the particle will have some world line. Right? So it will span a world line in the space, a world line of a point particle. So we ask ourselves, so how do we describe the motion of the particle? How do we describe this world line? And the most natural way, something that you use in classical mechanics, is to say, well, you gave us coordinates of the particle, and all I need to say where my particle is in space at a given instance in time, I'll just have to tell you what the coordinates are. And so usually what we have is we're going to say that our spatial coordinates x of I, okay, so those are our guys x of I, they are functions of x naught. Now the problem with that is x naught is special. It makes it forces us to choose one particular coordinate and declare it to be time. And eventually, one of the fundamental principles that we use in build up the string theory will be Lorentz invariance. Okay, will be Poincare invariance. And so, so what we want to do, we want not to have a particular coordinate have a special status. And so the way to do this is to actually make the description of the particle slightly more redundant. So what we will do is we do more redundant. So what we're going to do, we're going to choose a parameter tau along the world line, and so we parameterize the world line with an arbitrary parameter, and we're going to now talk about all d coordinates as the functions of this parameter on a world line. So, sorry, tau, where this is arbitrary parameter on a world line. Okay. So now think what happens, right? Right, so we want our description to be independent of the way how we do our parameterization. And so what this means that if we decide to go to a different parameter tau prime, then our coordinates x sub mu that depended on tau, they will depend on tau prime. And so what we will require that they do not transform. Okay, so it doesn't matter as long as I fix. If I choose this point on the world line, as long as I'm talking about that point, and that's what's related tau prime and tau, I will be describing exactly the same position in these space-time directions. So in other words, and this is a very important observation now, this x mu of tau are scalars on a world line. Right? So what you thought you were describing before, you were describing the motion of particles in these space-time dimensions, but once we went into this manifestly covariant way of representing the motion of the particle, we end up talking about a single coordinate, right? So you might say that we talk about one-dimensional classical field theory, and in this classical field theory, the coordinates of the particle become scalar fields. Okay, so coordinates are scalar fields of D equals one-dimensional auxiliary fields here. Okay. So is this clear? That's an important thing that I'm going to use. To build up extension to string theory. And that's actually, you can see the inklings how instead of talking about a high dimensional object, I can restrict and talk about much lower dimensional, and I should have exactly the same information. The idea here is to talk about the wall lines. Right? Okay, so very good. So once we sorted this out, so the next thing we want to do, we want to write down the action of the point particle. So we're going to assume that our point particle has mass m, right? So m is the mass of a point particle, and what we want to write action. We want to write action for this point particle. If you wish, we want to write down an action of this auxiliary one-dimensional quantum field theory. Well, it's not quantum. First it will be classical, and we'll quantize it later. Okay, so what are the requirements that we're going to impose? The first one is going to be Poincare invariance. Okay, so in other words, we're going to demand that whatever action we will write down is invariant under Lorentz transformations and translations of this d-dimensional spacetime. So when we have x mu, it goes to x mu prime, which is lambda mu nu times x mu plus a mu, right? So lambda mu nu are some constant matrices, right? So which are in so those are in SO d minus 1, 1 Lorentz group. So those are rotations there. And then in mu are just translations. So we're going to require that whatever action we will write down, right? Or if you wish, whatever field theory we will write down, and those guys are our fields. So what we write down is invariant under this Poincare invariance. And second, something that we definitely don't want to lose is reparametrization invariance, right? So the whole way of thinking about this as a theory on a wall line was the introduction of a parameter on the wall line, and we don't want physics to depend as to exactly how we introduce it. So the second requirement is reparametrization. Invariance on a word line. Okay, so what this tells you, if whatever action we write down shouldn't depend on reparametrization invariant, it must not depend explicitly. You think of it in a very mundane language. It must not depend on coordinates, and so it must be something physical. And the physical here means geometric. Must be a geometric geometric quantity. Okay, so that's if you wish, immediate implication of reparametrization invariance. So if I give you a pencil and that pencil has a length, how I measure this length doesn't matter. It is a pencil of that length. And that actually brings us to another thing. When we talk about word lines, a one-dimensional object, a quantity which has a geometrical meaning is the length. The length of a word line. Okay, and so the action that is doing precisely this, and in addition, we also want to have Poincare invariance. It's going to be this minus m integral d tau. So that's an integral over the whole line, and then I have minus x dot mu power 1/2. Okay, so what do I mean by x dot mu? So this is just d x mu with respect to d tau. So, so the fact that this action is Lorentz invariant is obvious, right? Sorry, Lorentz, well, actually Poincare invariant. Well, why is it Poincare invariant? Well, we have derivatives here, so the constant translations doesn't matter. And then the indices are contracted in the right manner, so that what I have here is a Lorentz scalar, so it will not depend on this lambda mu. So it indeed Poincare invariant. So this guy is Poincare invariant. And so what we need to do, we need to show very quickly that it's also invariant under reparametrization. So let's do that. Actually, if you open some of the books, so the one I just remember only one author out of 3. That was an old Russian book, Novikov. So geometry and physics, something like that. And so well, you can read it, see that that's indeed how you would measure the length of the whole line. So right. Do I need to show that it's reparametrization invariant or it's obvious? Yes. No. Is it obvious, guys? Obvious. Very good. So let's go ahead and discuss variation. So then I have delta S, so variation. So it's equal to minus m integral d tau. So I need to vary with respect to delta x. So I have minus x dot mu minus 1/2. So I have minus 1/2. Sorry, I have plus 1/2. And then I have, so I vary the square root, and then I need to vary the stuff inside. So there will be a factor of 2, because I have 2 x cubed, and then I will have the variation of
Alex?
Yep.
Question. When you say that this should be parameterization invariant, you mean that for any 2 points, the coordinate tau can change, but the length between 2 points and the coordinate x mu should not change, right?
Right. So I'm going to talk about this because this is very important, guys. That we, yeah, that's what I mean. So as long as I transform appropriately the endpoints, so altogether the length must be the same. So let me show that that's indeed. I'm going to do that. Just one line, right? So we're going to say that our tau prime depends on tau. So what I want to do, I want to write it down as x mu prime. Well, so x mu is x mu divided by tau. But now I have to think of this, that this guy actually depends on tau prime, right, in my new parameterization. So I can write it down as prime, right? So once it depends on tau prime, I have to put it prime. That's all I do. Divided by d tau prime, and then d tau prime divided by d tau, right? So what happens is that if I have this square root, mu is a 1/2, so you can see where it will go. So it will go to the same square root prime. Right, so now everything depends on prime. And then each x mu will bring d tau prime over d tau. There are two of them, and they take a square root. So I will have d tau prime divided by d tau. And then in front of this, I have d tau. So once I multiply the d tau, it will turn into d tau prime. And so I will have exactly the same integral, except depending on tau prime. And of course, if I do this, so practically what I'm doing is just change your variables in the integral. I have, as you pointed out, I have to take care of that and change the endpoints as well. But once that's done, you know, it's reparameterization invariant. Okay? By the way, you can see that it would not have worked. It would not have worked if I would have not a square root, but something different. Right? So it's also obvious because then I would have too many powers of d tau prime over d tau. So it will not turn back into exactly the same integral. All right, guys? So,
but any definite integral would have been reparameterization invariant. Like, because it's just
well, no. But the thing is that we impose a condition that our x mu transform as a scalars. So what you are saying is that yes, indeed, the integral will be invariant, but that will force x mu to transform.
Like scalar.
No, not like scalars. They will have different powers of d tau prime over d tau. Right?
Okay.
Well, I mean, if I will have different powers, and if I still want to make sense that, you know, it's the same action, then I would have to force those x mu's not to be scalars on the Bode lot. And that's something that we actually, for good or bad, we decided that that's what we wanted to do. Those guys are invariant. We will, when we talk, we will introduce additional fields that will have non-trivial transformation properties on the tau. That's an interesting aspect to discuss. I don't know if it's been studied and what would happen if you will introduce fields with space-time indices but non-trivial properties on the bullshit. But anyway, so we're dealing with simple ones. Okay, so let's go back. So we have, so we have this variation, and so let me get it together. So I will have m with a plus sign, but but now I want this guy involves a derivative with respect to d tau. So if I want in my variation to have just delta s, I will need to integrate by half. That will give me minus m d tau, right? And then I will have what I'm going to write down as u. It will have a derivative here, and then there is delta x prime, delta x prime, where this u is just minus x dot mu, 1/2, and then I have this. Okay? So is it obvious to you guys? Good. So we have this, and so you can see that the variation principle. So if we require that delta s over delta x mu equals to a constant, what that leads to us? That leads to a condition that u prime mu equals to 0. So what this tells us? This tells us that u mu is a constant, right? And so if you recall your special relativity, what is this u mu? U mu is just that whole velocity of a 4.5, right? So UU is whole velocity of one particle, and in order to see that, so if you do that, you will see that that's exactly -1, right? So if you, the square root will become just a vector, and it will cancel, I think I made a typo here because it's -1, so it will cancel with a contraction of x minus mu. And there is a -1 as required. For a full velocity vector, it must be a time-like because we have a massive particle. Okay, so what we discovered that in doing, so we talk about a particle of mass m, didn't have any interaction, it was moving in the ambient space, and we know that it has to move in a straight line. A physical way to say it, it must have a constant full velocity, and what we see right now is that the actions that we built actually predicts that. So, so one of the important things, and if you ask me where does exactly the 26 come in a string theory, so you will see that it comes in that the theory is scale invariant. It doesn't depend on any scale. Now, if we start talking about particles of various masses, there is a mass, and we want to get rid of it. So in other words, the quantum field theory of particles can be scale invariant to, at least in a perturbative setting as we discussed right now, only if particles are massive. If they are massive, well, there is a mass. Oh, so there is a problem with taking m goes to 0 limit. So everything that we talk up to now doesn't make sense because the action goes to 0. And so what we need to do, and effectively the reason I'm leading you this route because that's what we're going to do for a string, right? So we would like our string not to depend on when we write down the action. We want to write it down in such a way that it would be sort of sensible. Some of the excitations of the string must be a massless particle. We want to have light states. Okay, very good. So how do we do that? So we saw that in order to make things more symmetric, okay, we do it at the expense of introducing additional fields, and that's what we're going to do here once again here. So we make description more redundant. So in particular, we're going to introduce a metric on a wall line. Okay. So we're going to do more redundant by introducing arbitrary metric on the wall line. What do I mean by that? Well, let me give you some idea from GR that you're familiar with. So in GR, if I have an integral of a space-time, x1 dxd, right? So that's a particular choice of a coordinate system, and I might like or I might not like this. So this measure, the measure of integration, is not invariant under diffeomorphism, and one way to make it diff-invariant. So now I can go to diff-invariant coordinate, and so what I have to do, I have to introduce a metric, okay? And so now my measure is explicitly invariant under change of variables. So if I were to do this in a context of one dimensions, then so the metric will have a single component. I'm going to call it eta. It can depend on tau. And so introducing a metric so now it must transform as a metric. So what this means is that d tau times eta of tau, once I go to a different coordinate system, will be d tau prime, eta prime as a function of tau prime. Okay, so now what you see the examples that we sort of glossed over when we talked about possibilities of different actions there. So here you have what we did. We introduced additional field. So additional field on the load line. Okay. And know that that additional field, it's not a scalar anymore. Once we make reparameterization, once we make a different choice of our parameter tau, eta prime will transform. And so eta will go to eta prime, which is equal to eta d tau over d tau prime. So it explicitly has transformation properties. Actually, it has the right transformation properties as necessary for the tetrad, sort of analog of the square root of minus gz. Okay, very good. So we introduce this extra field, and so what we want to do, we want to rewrite our point particle action, including this additional field, and we want to have the same properties. It must be invariant under Poincare transformations, and it must be reparameterization invariant. And so I'm just going to write it down. And then we will study it. So I'm going to write it down as a prime action. So as prime point particle. So it's equal 1/2 d tau eta minus 1 x prime mu minus eta m squared. So again, the logic that we're doing here is that we already agreed what is our point particle action. It gave rise to the right equations of motion, had a nice geometrical meaning, but it had the problem with m goes to zero limit. And so what we wanted to do, we want to write down the action that has all the properties as above, and so must be, once I said this, so this must be equivalent, well, at least classically, we'll go and talk about this in a little bit, at least classically, to the point particle action that we discussed above. And additional condition is that it must have a well-defined limit as we take m to 0, and so you can clearly see that that's indeed the case. Okay, so again, Poincare invariance obvious. And so what we need to check, because the combination there is a Poincare scalar, so what we need to check, we need to show that this guy actually transforms as appropriate under change of variable. So we're going to make tau goes to tau prime, which depends on tau. So we'll just repeat the same discussions that we did before. So let's see what will happen. So again, x dot mu is going to be equal to d x mu over d tau. This is d x mu prime over d tau prime, d tau prime over d tau. So there is no change. there is no change here. But then eta is going to be equal. Now I have to look at the transformation properties here. So eta is going to be equal to eta prime times d tau prime divided by d tau, right? So now let's see what our object inside is. Eta squared. Right, so now what I want to do, I want to rewrite it in terms of this prime variables. So it will be eta prime minus 1, right? And then I have to invert this, so it's d tau over d tau prime, right? And then I have two powers of x mu prime, so it's going to be x mu prime dot x mu prime dot, and I have each of them will be d tau prime over d tau, d tau prime over d tau squared. And then I have m. M is a mass, and so it must not transform. It's a scalar, right? Under change of parameter along the low line. So then I have minus m squared, and instead of tau, I will have tau prime, d tau prime over d tau. Okay. So now you can see that, so there is a second power here, but it will cancel with one there. So there will be just the first power here, first power here. So all this bracket will turn into identical bracket with d tau prime divided by d tau. So we choose all variables, the old fields, and rewrote them in terms of transformed fields. The price we paid is this d tau prime over d tau, and you can see that that tells you that s prime of tau prime as a function of tau is going to be exactly the same as a function of tau. Right? So we show that it's reparametrization invariant, assuming that x mu's continue to be scalars. And this guy, eta, is not a scalar, but it transforms in a very specific manner. Okay, so the thing to note is that this eta is not, even though I keep talking about it as being a field, right, on the world line, it's actually not a dynamical field. So tau as a function, eta as a function of tau is not a dynamical field. It's more like a constraint, right? The reason for that is because action does not contain tau dot, right? So it's the appearance of time derivatives that points to dynamical character of variables, and so we don't see it here, so it's a constraint. And so what we're going to do, because it's a constraint, we can solve for this constraint and plug it back in the action to see what will happen. So what we can do in a field theory language, what we're going to do, we're going to integrate out of the constraint. Okay, so some of the things that I am saying here actually is very important. So the fact that it's not a dynamical field, once you start writing, so it's not allowed to fluctuate. Okay, that's in other words. So in some sense, it's more like a Lagrange multiplier, right? So let's solve this constraint. So, but it's arbitrary. So the important thing is that it doesn't allow it to fluctuate, but it's arbitrary. Okay. So let's see what kind of equation of motion it has, right? So what we're doing, we're integrating it out. We're finding its equation of motion and plugging it back in the action. So that's going to be the equation of motion. So we look at the action, right? So what do I see? So I see, I look in the Lagrangian, I see eta minus 1, so it becomes minus eta minus 2 x dot squared with a minus sign. No, it's plus sign. So actually what? Minus. Let me keep writing. So there is a minus there, so I want to put minus inside here. And then there is eta there, so that's minus m squared, and so that must be equal to 0. So the equation of motion for eta, for our head rate, so eta is going to be equal to minus x by u, which is 1/2 divided by m. Okay. Now, as I said, it doesn't allow it to fluctuate. So because it's a constraint, it must have this value. Okay. So it keeps this value, and the fluctuations in eta are not allowed. And so now once we solve for the value of eta, it must always take this value. So we can go ahead and plug it back in our S prime point particle. So what we did, we put we solved for eta, right? I substituted eta in. So I have 1/2 integral d out, so you can just follow there. So I have eta minus 1. So it's going to be equal to m times minus x dot u minus 1/2. And then I have to multiply it by x mu dot mu, right? That's one piece. And then the second piece, so m squared will cancel with 1m in the denominator. So I will have minus m, and then I have that minus x prime mu, which is 1/2. Okay. So now notice what happens. So there is a minus here, there is no minus here. I put a minus here. I put a minus in front. Okay. Now minus 1/2 with this will cancel, and so I will have this guy with a plus 1/2. And those two pieces are exactly the same. There is a 1/2 in front, so it's going to be equal minus m integral over d tau minus x prime mu to the power 1/2. So what we did by introducing this additional field eta on a walled line, we managed to have a nice m goes to 0 limit. So now our action can also describe massless particle. And what we showed is that in the case of a massive particle, it's actually equivalent to the original action we started with. So we achieve all goals. Any questions? Yes.
Actually, eta was already in the previous section, right? It was not mentioned explicitly, right? Because an integration is not defined without a metric, right? I mean Jacobi, right?
Well, see, that's something that we went, right? So
yes.
in principle, you're right. But at the end of the day, we wrote the actions that's invariant under reparameterization. What you are saying is that there are Jacobians once you do change of variable. And what we show that in the first actions that we wrote, there are no Jacobians needed. Right?
No, there is Jacobian, but it is not mentioned explicitly. I mean, when you make a coordinate transformation, you do the same thing. You change the Jacobian and you change the transformation, then you cancel these two terms.
If you wish, yeah, the fields, you know, the way we wrote the action is that the Jacobian arises because we had the derivatives of the scalar fields. So the Jacobian arose from there, and it cancels the Jacobian due to the change in time. So that's correct. And so this action is not different, right? So in fact, we explicitly demonstrated that it's identical.
Only thing I don't understand, I mean, what do you do by this condition? I mean,
Which one?
you are promoting eta to be a field, and then you varying the action and minimizing, and you're getting the condition for the.
Yeah, and so that's think of this as equation of motion for the eta, right? So I find out that
Imposes a condition over, I think, the kind of transformation you can make in the, because Jacobian should always be this.
Right, so the Jacobian that you're talking about is simply d tau prime over d tau. That's all what it is. Because when you go in the integral from d tau to d tau prime, the Jacobian is d tau divided by d tau prime. That's all the Jacobian. And you're right that we need to absorb that Jacobian in the transformation of our fields. So the point is that we decided to have x mu being scalars. Okay, so it doesn't transform under tau transformation. So, so there are two possible ways to proceed. One way to proceed is to make an action that involves the square root, right? So we discussed that we need to have that square root. The reason we need to have that square root, otherwise the Jacobian from the square root will not cancel the Jacobian from the mesh. We're not talking this terms. So, but another thing, so now we wrote a different action that doesn't contain the square root. So you would have said, well, it doesn't contain the square root, there is no way you can do it. And we showed that, no, it is possible. So I have to be more specific. We cannot do it provided that we keep x mu's being scalars, right? So now what we showed is that you can do that, but the price you pay is that you have to introduce additional field and assign a special property, special transformation property for that additional field. That's your eta.
And you have the condition that comes from the minimization of action.
That's not, again, I don't like to think of this as a condition. So now it becomes additional field, right? Some of the fields in your field theory can be dynamical or can be non-dynamic. Non-dynamical are just, something that are frozen to the values determined by the equations of motion. So actually, if we talk about classical field theories, there is no difference because nothing can fluctuate. The difference can come only quantum mechanically, right? Which we haven't started. See, what would have happened quantum mechanically if, so classically, everything that I say, there is, I shouldn't even distinguish this dynamical versus non-dynamical, right? The point is that, if I will still have equation of motion, so I could have solved for the dynamical field and plug it back in the action. And the question is, will that thing make sense quantum mechanically or not? So my point is that if you do that for the field, which is dynamical, that doesn't make sense because there will be quantum fluctuations. Okay. Now, if you have a constraint, you can always do that. So in other words, you can always solve for a constraint and plug it, and it will take. So that thing to what we did right now. So in other words, this step is actually consistent even quantum mechanically. So if you wish, what I can say here is that we have two actions: one involving the square root and one without the square root. And those two actions, if we now will go ahead and quantize the particle, are equivalent for massive particles. Right? For massless, it doesn't make sense to talk about quantum, right? And the reason for that because that was a constraint. So eventually, so there are two. I mentioned only one reason why we talk about this action. One reason is that to go into the angles to zero limit. But there is another reason, which I'm implicitly emphasizing over and over, and that's the square root. You hate to deal with the effective actions that have a square root. Such actions typically don't have a well-defined perturbative inspection. So you don't know how to set up your Feynman diagrams and all these perturbation series. And so what you always want to do, you want to have action. See, the beauty of this action is that in terms of dynamical field, it's quadratic. It's a simple free quadratic theory, Gaussian asymptotic, if we talk about asymptotic. The one with the square roots is difficult to deal with. You wouldn't know if I give you a path integral with the square root of the functions inside, you wouldn't know how to deal with it, so you would be forced actually to do it this way. Okay? Now, what happens when we discuss strings, it turns out that we'll go exactly the same rule. The reason is that if I were to ask you, can you guess this action? And the answer is no, it's difficult for you to guess it because you have to think about it. Actually, guessing the one which I wrote before, just the length of the word line, it's a geometrical object, so you can immediately do it. Okay? And actually, when we talk about the string, we will derive the square root action first because it will be so easy. And you can see, everything that I'm going to talk now about the string, you could have done for the point particle. And that's how you would get the length of the word line. It would have been exactly the same word. So that's one that is easy intuitively. It's immediately obviously parameterization invariant because it's the size, it's the measure. But getting this one is more difficult. Okay? So that's what we're going to do. So we're going to go first get the bad actions, the ones that we will never work with. And then we will get the one that we will discuss, sort of the analog of the quadratic action in the fields. And then when we do quantization, again, it all boils down into quantization. Square root action, I don't know how to quantize. Okay, this one I know how. And so what we're going to do, eventually we're going to do quantum mechanics. We need to do quantum mechanics because otherwise we will not see any of the beautiful features of string theory that I was mentioning. So let's go talk about the string now. Very good. So I suggest the following. So let's make a break, not now, but in 15 minutes, for about 10, 15 minutes, and we'll continue until 1 p.m. Very good. So we talked about point particles, and now we're going to do the same. Now we're going to move to a string. Okay, so I'm going to talk about open string first. Well, so there are two types of strings, but open one is easier to deal with. I mean, at this stage. We're going to talk about open string. So open string is an object that has two ends. Right? So again, I have my spacetime. I have my spacetime x, which is x1, x1, and I have my time. And so instead of having a point particle, I have a string, but the string has two ends. So if I ask, how does my object evolve? All I have to do, I just have to follow the evolution of the endpoints, right? And so this, I can call this sigma. Of course, I have to introduce additional coordinate now. So now, as my endpoints evolve, I have a two-dimensional surface that is being spanned in space-time. So I need to introduce coordinate along the string. So it's going to be sigma. Sigma goes from 0. Sigma goes to L. And so here, I can say that this is parameter tau equals 1. This is parameter tau equals 2. This is parameter tau equals 3. So kind of thinking in terms of parameterizing the endpoints of the string. Okay, so again, in order for me I want to be able to tell how exactly my surface lies inside this two-dimensional spacetime. So coordinates in a spacetime are again x mu, and so now the only difference from the point particle that this x mu is going to be a function of two variables. It's going to depend on tau, right? So by the way, this tau, I don't have to, so this is tau that lives at sigma equals 0 world line. This is tau that lives at sigma equals L world line. I can choose, sigma equals L over half world line. And it will have, well, it's all I'm mumbling here is that it's a function of two variables, okay? But the point here is that, so now it shouldn't be a surprise to you if I say that this X mu is a field that lives on a wall sheet, right? So it's a field of 1 plus 1 dimensional wall sheet field theory, right? So now, now the motion of a string is described by this auxiliary field theory. And so our step here is going to be the same. So what we would like to do, we would like to write down the action describing describing either the motion of the string in the dimensions, if you wish, or the action of this 1 plus 1 dimensional field theory. So how we're going to do that? Well, so the obvious thing to do is to say that is again, well, first of all, we want two conditions: Poincare invariance. That's one condition. And second condition, we want reparametrization invariance. And reparametrization invariance is somewhat more complicated because so before we had a single variable, so now we have two variables on the wall sheet, tau and sigma, and so both of them can transform. And as they transform, they can depend. So it's a more complicated function in general. So something that immediately will give us the parametrization invariant object here is the area of the wall sheet. Right? So before we talk about the line, which is a natural geometrical object of a one-dimensional object. So here, the parametrization invariant forces us to talk about area of a wall sheet. So how do we measure the area of the wall sheet? Well, this is something I asked you involve your favorite notebook, and you answer me yes. So if I have the metric on the wall sheet, HAB, so what this means? This means that if I measure ds squared on the wall sheet, I will have HAB, DYA, DYB, and so the area of the wall sheet, is going to be equal integral d tau d sigma square root of minus h, where h is the metric, determinant of the metric on the wall sheet, right? So h equals determinant of h ab, right? And the minus sign is because our wall sheet must be timeline. Because it must be, well, it should be correct. So any questions up to here? Is it clear that that will be the area?
Is it possible to take derivatives with respect to tau and sigma and maybe make wedge products instead? Or?
Eventually, we will ask the question, what are the fields? And there will be additional term that presumably you can rewrite down like that. The problem with wedge products is that they are topological terms. What that means, that a fancy way to say is that you add extra terms, but they don't affect your equation of motion. So that will happen exactly in this case, running a cat. So we'll do this, and then we'll find out that indeed there are some other terms that we can write down, but those terms doesn't modify equation of motion, but those terms will be important when we talk about various topologies.
So is it see those as transcendence terms then, or something like this? Or?
Well, okay, so there is a potential. I'm saying there is a potential. The ones that we're going to write down, well, I maybe it can be written in terms, but there is definitely a transcendence. There is a true form that lives on the wall. That's additional extension, right? So it will depend. So it will have the structures of wedge product. So the thing here that I want is what's special about this action and why it's a natural point to start is because it's a reparameterization invariant in an obvious way. It depends on the area. We can ask questions as to are there any other fields? So that's something that we'll talk later.
The metric H is the induced metric on one sheet from the Minkowski metric.
It does, and that's exactly what I'm gonna do. So the way I said it now, so you give me a metric on the wall sheet. That's what's gonna be the area, right, of this wall sheet. But now we do precisely this. We're gonna ask what will be the natural metric on the wall sheet once it's embedded in this ambient spacetime. And by the way, everything that I'm doing here, you would have done for a point particle. So your starting point would have been that, well, there is a metric on the wall line. I'm just going to write it down, d tau square root of the metric on the wall line, and you would be asking exactly the same question, what is the induced metric on the wall line? So how do we figure out that? Well, so I'm just going to, what we need to do is we need to compute HAP, which is the induced metric on the wall sheet. And the way we're going to do this is the following. So there is a very simple way. So if I'm going to write down the line element in d dimensions, so it takes the form eta mu nu, right? So that's our Minkowski metric. Eta mu nu times dx nu. But now our x nu and x nu depend on wall sheet coordinates. And so what I can write it down, as so dx nu, it's going to be equal to, write it down as del x mu over del ya dya, right? So where right, so ya is tau and sigma, right? The coordinates on the wall sheet. And so you can see what happens here. So in other words, I'm looking how would my line element look like. So this is a way how line element, how I could measure distance between any 2 points in the ambient space. But what I'm doing now, I'm putting a constraint. Suppose that my points are not anywhere in this ambient space, but are restricted to this surface. And so what this tells me that these axes are not arbitrary, but they depend on the coordinates twice a day. Once I said that, then dx mu is given by this simple relation. And so you can see that in that case, the line element in d dimension takes its form, eta mu nu del x mu over delta ya del x mu over delta del yb dyb. Okay? So now the point is that we don't want to invent any additional metric. The idea of induced metric is sort of the natural metric that's determined forced on you from the ambient space. And so you can see that what that tells you, that combination must be your induced metric. So we are done. Done, guys. Because okay, good. So our action for the string has the name number root of action. The name given by Nobel Prize winner. It's here. Nambu from Chicago. So I'll write it down as -1 over 2 pi alpha prime, and then the integral over manifold M. So this M is a surface spanned by the wall sheet. And then I have here d tau d sigma square root of minus h, right, where this h, AB, is equal to del x mu over del ya del x mu over del here, del YE. Okay. By the way, now it should be obvious to you that I could have said everything I said here in one dimension, and I will got exactly the square root actually was 0.1. Okay, so very good. So now you see the appearance of always below alpha star. And the reason why it appeared here is because we want action to be dimensionless. Once we make a path integral, our path integral, we're going to exponentiate the action, so it must be dimensionless. And so the way to make it dimensionless, so the metric is dimensionless. So here we have 2 powers of length, so we need to divide by 2 powers of length, and alpha prime is precisely what will provide you 2 powers of length. Okay. So as I said, and that's why you see this useful combination 2 pi comes in. So that's also denoted as T, and it's known as the tension of the string Wolchi. It has the same kind of meaning as a string. You can think of a string as a rubber. So if you stretch it for some distance, it has some size. There will be some energy stored in this. So the same thing goes in here. So there will be a tension. So if you stretch something, there will be an energy associated with it. And so the tension is the prefactor of the action. All right, guys. So let's see. So is it obvious that it's Poincare invariant? The answer is yes, right? Because it's everything we did was Poincare invariant, right? We wrote a Poincare invariant line element, and everything went from there, and indices are contracted in the right way. Is it reparametrization invariant? The answer is yes, because it has a geometrical meaning. It's the area, and I'm not. In principle, I could have done the same what I did before with a point particle, but it will be a repetition. So if you allow me, I'm not going to do that. So it satisfies all the right property, but it has also a very bad property. And the very bad property of it is that it actually it is a square root action, and so as I was telling you before, I don't know how to make sense of square root action. So the same falls in here. So what we need to do, we need to find an analog of SPP prime, right? Remember that SPP prime was the action that was a nice action without any square roots. An analog of that to S Nambu-Buto. Okay? And so the idea there is that, so remember that now it becomes clear that once we write down the square root actions, the metric becomes induced. And so you might guess, and so eventually what we did, we introduced additional redundancy by, so let me write it down. In point particle case eta was arbitrary metric, so sort of playing the role of arbitrary metric. And it's only when you impose equation of motion on that eta, you get exactly the induced metric. So the idea here is, in here we started with an induced metric, and now we want to be a little bit more redundant, and we want to introduce arbitrary metric on Wolchi. Okay, so the philosophy is sort of similar. There we get rid of all the square root problem by making a non-induced metric. So we're going to try here as well. And so now our action, besides the field mu will depend on a Wolchi metric gamma AB. And I'm just going to write down this action. So it's -1 over 4 pi alpha prime, and then the integral with respect to m tau d sigma square root of minus gamma, and then I have gamma AB del A f mu del B x mu. All right, guys. So let's talk about this action. So first of all, the good thing is that you see that indeed our scalar fields acts antiquadratically as we wanted. By the way, this action is known as a Polchinski action, so I'm going to call it SP. So I don't know why, and I don't know. It wasn't Polchinski who suggested this action anyway, but it was suggested by some other guys. But the important thing is that Polchinski was the one who strongly emphasized the importance of this action when you do quantization. And the reason for that, again, there are no square. So let's look, let's discuss symmetries, and then we'll go for a break. So again, our favorite symmetries are Poincare invariance and reparametrization invariance. Okay. So the Poincare invariance simply forces us to have correct contraction of indices. All the indices must be contracted with Minkowski method. So here I have mu, and it's contracted with eta mu. So it's Poincare invariant. Okay. So reparametrization invariant requires us that the integral has an invariant volume, and then it integrates over something that's a scalar. So let's see that that's the case. So what I have here is invariant volume. So this invariant on the reparametrization invariance, right? So this is invariant. Well, it's not a volume in this case. It's invariant area element. So this precisely is the square root that will produce the Jacobian of the change of variables that will cancel the Jacobian here when you do change of variables in this integral. So this by itself is reparametrization invariant. And so what you need is whatever is left is invariant on the change of variables. And that's guaranteed if you know the GR, right? And I asked you and you told me, yes, we know all from the beginning till the end. So that requires that the curved space indices are contracted with the background metric, and you can see that that's indeed the case. A contracted with A, lower upper, and so that must make it really reparametrization there. Right, guys, so let's take a 10-15 minute break, and after that, we'll go ahead and show that actually this action is equivalent to Nambu-Buto action. And after that, we will be discussing some symmetries. Yeah. Right, so it's in 10 minutes. 10, 15.